Okay, so welcome all to today's ICT String seminar. Today's speaker is going to be Alok Laddha from CMI, and his talk is going to be on positive geometries for scalar amplitudes. Welcome, Alok.
Thanks, Naveen. Thanks to everyone.
Just a second. I request everyone else to be on mute, and if there are any questions, please unmute yourself and ask them. Great. Sorry, Alok. Go on.
Okay, yeah, thanks. So, yeah, just a small disclaimer that since this is a kind of relatively new subject, please, I've tried to not assume anything, but you feel free to ask me at any point. And also, my handwriting is not very good, but no. So please, if something is not clear, please also feel free to ask. Some of the slides which have a lot of text, I've put it, I've typed them. So, okay, so this is the title of my talk. I mean, if the words are not, the positive geometry, the word is not familiar, please, don't worry, hopefully it will become clear in the talk. And some of what I will say is based on recent and sort of kind of never-ending work that I've been doing for the last few years with Mrunmayee, who is now at Caltech. He just joined as a PhD student there. Actually, he's much better equipped to give this talk than I am. But a lot of what I will say will be kind of a review, and that is based on some of these seminal papers. I just wanted to list them before. So that there was this paper which in some sense started this entire activity of positive geometry and asymmetrics in non-supersymmetric quantum field theories by Nima, Bai, Song, and Yan. And then there were a few papers by mathematicians to kind of formalize sort of the structure that KBHY observed in their paper, which are the three papers that I've listed here. And finally, there was a paper in 2019 by Nima, Song, Salvatore, and Thomas, which also influenced a lot of the work I did early this year. Okay, so maybe I just start first with some motivation. So just to understand what the goal of this, amplitude. I mean, this program is sometimes called positive geometry program, also broadly known as the Amplitude program. So last 2 decades, we have seen a number of striking, but in some sense disparate advancements in our understanding of the asymmetrics in quantum field theory. So, for example, the first, in some sense, like in the recent times, a big advancement that happened is where it was shown that at least for a class of theories, 3-level scattering amplitude can be built out of on-shell 3-point amplitude, and we don't need any sort of other information. And these are known as BCFW or engendered recursion relation. But this advancement also came with a little bit of a surprise that locality was not manifest in this recursion relation. So in particular, if you have seen them, you know that, if you look at the final answer, individual terms in this final answer have what are called spurious poles. Those are poles which are not consistent with locality, but such that in the full amplitude, if you sum over all the spurious poles, you get 0 residue. So of course, the final answer is local. So this is quite different than the way we compute asymmetrics from Feynman diagrams, where locality is manifest at every step of our computation. Then, but there was even a more sort of striking representation of asymmetrics, which was proposed by Cachazo and Yuan in 2013, I think, which sort of we can call it a worldsheet representation because it was very much inspired by string amplitudes. And in this representation, even unitarity was not manifest in any direct sense. But it turned out to sort of emerge from a property of the geometry of this underlying space, which was something called moduli space, on which amplitudes were represented, in fact, not as functions, but as some kind of differential form. So it's not important for us, the CHY formalism, but just wanted to give you an example of a new representation of asymmetrics where even unitarity was something that emerged as the consequence of something deeper. And of course, probably like one big huge surprise which has emerged in maybe last 10-12 years is that for a wide class of theories, scattering amplitudes admit a representation which is not at all manifest in Feynman diagrams, in the sense that there is a hidden symmetry which is known as color kinematics duality. And it's a duality which is manifest in what is called a BCJ representation, but not if you write the amplitude as sum of Feynman diagrams. So kind of the very broadly stated goal of the positive geometry program, or this program where you try to understand asymmetrics from some geometric objects called polytopes, is to sort of unify all these disparate representations into hopefully a deeper formulation. So the idea is that we want to start with a minimal number of postulates because we want to derive all these all the nice properties we get in CHY and BCJ and BCFW from from a deeper formulation. So we don't want to assume too much. So, but then we don't have much to go with. So, obviously, if you want to compute amplitude and we don't want to assume much, then the minimal thing we can start is space of scattering data. So, for example, say, if you want to look at scalar quantum field theories, which is the only thing we will look in this talk, then we start with external momenta. And suppose we assume Poincare invariants, then of course, the only structure we have are the Lorentz invariant or Poincare invariant quantities we can build out of the external momenta. And then, it's not a very interesting space in some sense, but there's a question which has always stood for in the aesthetics communities that, on this space, what are the class of functions which qualify as a S-matrix? And I should just point out that this question is actually not trivial even at tree level. So, of course, people who are familiar with BCFW representation know that we have a representation where the amplitude has spurious poles. If I just give you some function which has this spurious pole, it may not look like a S-matrix of unitary local theory, but in the end it is. And the other, a little bit like a dumb example is, if I just give you a function which is given this equation 1, which has just the pole in the S and the T channel, obviously you may think that this is not a tree-level amplitude for any theory, but it turns out that this is actually, what is called a color-ordered amplitude in a specific scalar field theory, which is called the bi-adjoint scalar field theory. So just to even deduce what functions classify as S-matrices is quite a non-trivial question in general. So in this talk, what we are going to do to understand this program, this positive geometry program, is going to look at scalar scattering amplitude, in which the external particles are massless and have color degrees of freedom. So I will not assume that the propagators are only massless, although in the first half of the talk we will look at purely massless theories, but then we will see how the program generalizes if we have other fields with masses, for example. And I just should emphasize this masslessness is just for technical simplification. It's something which at this stage which can be generalized. But the color is not a technical simplification. It's something we would need. We would have to assume that the theories have color. So, and the reason we need this is because, if we have the external particles have this color, then as is known, we can work with what are called color ordered amplitudes, or in other words, planar amplitudes, where lines do not cross each other. So this planarity is of course nothing to do with the large n planarity, but just the fact that every amplitude in such theories can be built out of amplitudes where you can draw a Feynman diagram on a plane. So that's why we call them planar amplitudes. So basically these are amplitudes in which ordering of the external particle is fixed, and they basically span a vertices of an n-gon in a given order. So okay, so if this is our if these are the class of theories we want to look at, where we have color and we have scalars, and then if we assume only Poincare invariance, then we don't have, as we discussed, don't have much structure to go with, except that we know that we should work with Mandelstam invariants, or generalization of Mandelstam invariants for massless particles. And so with that, what we get, assuming planarity and masslessness of external particles, kinematic space, like a space in which we want to analyze S-matrices. And this kinematic space has a nice basis, and this basis is basically spanned by what we will call XIGs. I mean, they are known as planar kinematic variables, which are just defined here. So you just sum from the ith momenta to j-1 momenta, and these XIGs have a nice property that xii plus 1 is obviously 0 because pi square is 0 because the external particles are massless, and x1n is 0 because of momentum conservation. So because pn square is 0. And the reason this is a nice basis is that any propagator in a planar diagram will always have the form 1 by xij if you just meditate over any planar diagram. So it won't, you will never get a propagator which is say 1 by xij plus xkl, and that's why it's a very convenient basis to look at planar amplitudes. So by the way, please ask if there's any question at any stage. So let me first now fix some terminology. So if the scalar has, we are going to assume that the scalar have color indices, and the class of theories which have been looked at mostly for various reasons are where scalars have actually 2 color indices, and these are called, that's why they're called bi-adjoint scalars. And because they have 2 color indices, these amplitudes require 2 orderings in principle. So I indicate this ordering as sigma and beta, which are just permutations over the labels 1 and n. And for most of this talk, we will work with the ordering where both the color indices are in the standard canonical order, just say 1 to n, and we will refer to them as planar amplitudes. So in very few places we will focus on this more more convoluted objects where you have different ordering for the two colors. Mostly we will just work with where we have fixed ordering for both the color once and for all, and that's it. And so that basically what that means is that, so let me just say one example of what planar amplitude means. So we just fix an order, so that once we fix an order, we get like a n-gon, in an abstract n-gon, nothing to do with any physics. And if you look at, say, the massless phi cube theory, planar amplitude. So I fix the order 1, 2, 3, 4. Then I only get some more two Feynman diagrams, because the U-channel diagram has a crossing. It's not preserving this order. So that's the example of a planar amplitude, right? This amplitude. So in a general scalar field theory, of course, this is not a good amplitude. But if I have color, then this is what we call a color ordered amplitude, in the sense that once we fix the color ordering of the external part. Yeah. So now let me first give you the basic skeleton of what this program is, and then we are going to go into details of the steps of this program. And in some sense, this program can be divided into 2 or 3 steps. So so far I want to emphasize we are just starting with this space. So we don't have any theory in mind or anything, but we have assumed that we have massless scalar external states and they have color and we have Poincare invariants, and that's it. Now it turns out that just with this with almost no structure, we will see that there is a class of polytopes. By polytope, I just mean higher dimensional generalization of a polygon. So nothing too fancy, which we will call, which we will denote as ACD, where D is the dimension. You will see why AC, what AC stands for, which just exist. So these are just some polytopes which just live in the kinematic space. And so the reason these are interesting polytopes is that each of them induce, these are just some math result that they induce a unique differential form of the same rank as the dimension of the polytope on the same kinematic space. So right now it looks like we are very far from physics, because we just started with the kinematic space. We found some polytope, and under some technical conditions, we will see that these polytopes give us a form in this kinematic space. But then it turns out that if we take this form and we just restrict it to these polytopes, so we just look at the evaluation of this form in some sense on this polytope, then they start generating for different choice of this polytope. This in any phi to the p theory, where phi can in principle have mass m, just for simplicity, we will look at m equal to 0. So this is the rough structure of the program that we will look at it in much more detail. So yeah, so here I just want to say something that, but this program also gives rise to many questions. One is that we haven't put any asymmetric input here in locating these polytopes. So as you will see that these polytopes are located using some results in math, which don't know anything about any physics or asymmetrics or anything, but they come with very specific shapes. And in some sense, the shapes are such that they can be very complicated, higher dimensional polytope, but normal to each face of this polytope is always, in this Xij basis, they have components which are either 0, plus, minus 1. You don't get normals which are, with any other angles. But then we can ask, okay, why only these polytopes? I mean, in some sense, there's a tension that we know that in quantum field theory amplitude, there is a continuity due to the fact that we can deform couplings continuously. So the fact that these polytopes come with this discrete data, like, how do we understand this connection between continuous deformation of an amplitude by varying couplings and the fact that there is no continuous parameter here so far. And of course, there's another question that if you look at, say, a massless phi-4 interaction, which is generated by, say, one polytope in this case, but we know that we can obtain that interaction by integrating out a massive field in a cubic interaction of the type, say, phi square psi, if psi is massive. Then we would like to understand what happens to these polytopes now, because we have one polytope for one interaction, the other for other interaction. Then how are they mapped from by each other? I mean, can we understand this process of integrating out through this geometric picture? So these are like the sort of 2 questions we will, after reviewing the program, we will focus on these 2 questions in the talk. So maybe I should stop here and see if there is any question. I mean, this is kind of a broad introduction program. Okay, I will just proceed. Yeah, but please stop me. So let me now first we just go a little bit more detail into this kinematic space, which is just the space of generalized Mandelstam invariants. And now we had this 2-3 step program, and I want to explain to you in some detail how this program sort of built this program. So if the dimension of spacetime, I mean this kinematic space in general is a little bit complicated if we fix the dimension of spacetime, because then the Mandelstam invariants are not independent of each other and they satisfy very complicated nonlinear relation. But just for simplicity, let's say that we fix the dimension of spacetime to be larger than the number of external particles. Then it turns out that this kinematic space dimension is just n into n minus 3/2. It's a very simple linear space which is spanned precisely by these xij's. So then there is no constraint between xij's; they are just independent, and you can easily do a counting to see that they also are equal. That they are equal to n into n minus 3/2. So they form a basis for this kinematic space, as long as the dimension of spacetime is larger than the number of particles. But this is a assumption that won't make a difference in the end, because tree-level amplitudes for scalars are agnostic to the dimension of spacetime. But the reason this space is also interesting is that they have a natural, combinatorial or geometric meaning, that because we have fixed an ordering and we have this abstract n-gon. So if you have 6 particles, we have the 6 gon. Then, and you can see that all the xij's which are not 0 are internal chords of this polygon, because we know that xii plus 1 is 0 and x1n is 0, but everything which is non-zero like basically dissects the polygon into small cells. So I just give an example here of this dissection, and it turns out that just based on the fact that we have these dissections, we can start building some polytopes. So really nothing so far with physics, but it gives you very interesting structures. So this is a theorem that yes.
Hello, sir.
Hi.
Yeah, I should have asked this when you stopped, but just to make sure I understood when you this thing. Yeah, so is this supposed to hold for just a single species of scalar field with a specific potential like phi to the p, or can it accommodate several species? I mean, in addition to all the color indices, some other flavor indices and different couplings. I mean, a whole space of couplings.
Exactly. So the thing is that the polytopes that mathematicians give us amplitude for monomial scalar interactions with a single species. So lambda phi to the p. Okay. And now but the question was that that if you have more complicated, exactly as you're saying, like a polynomial interaction with generic couplings, then what is the picture then? I mean, then and especially if the couplings continuously vary, do we still have some polytopes which give us amplitude? I mean, exactly. That's the question we would like to sort of answer. So the discrete data, the discrete polytopes mathematicians give us amplitude only for scalar theory with monomial interactions.
But you have to kind of put them together in some way to try to generate.
So there are two. Yes. So there are two things. If you want to look at polynomial interaction with one species only, as you are saying, then there is a concrete way to put them together in a family, what is called a closed family of these polytopes. And you can use those family to generate. So the same polytopes can be used to generate amplitude for such theory. So there's one scalar, I mean, modulo the color, but there's a polynomial scalar interaction. But now you can ask, what if you have, two scalars with different masses, for example? Then the situation is that you really need to Then these polytopes as they are do not suffice, as we will see, but there are interesting new polytopes that that give generate amplitude.
And thanks.
Hi, Alok. Sorry, I also have a question. It's actually about the slide a little later. It's just about the comment you made. So you had this kinematic data, which I thought was ki.kg, right?
I built out of, I mean, So it was the
SIGs.
SIGs, yeah.
Yeah, good. And then right. But then at some point you made a comment saying this is agnostic to dimension. But of course, there are these nonlinear constraints on SIJs if you take I and J to be large, right?
Yeah, exactly. So the point is that if you fix dimension, like say 4 dimension, then the dimension of kinematic space is 3n minus 10. So it's these xij's are not independent and they satisfy the so-called Gram conditions. So that makes the things more complicated. But what we will do now is to assume that the space-time dimension, it's a very unnatural assumption, as of course at this stage, that the space-time dimension always larger than, so we can think of it as infinite dimensional space-time. But what saves us, at least in this case, is that we are dealing with scalars. So the tree level amplitude for scalar it doesn't know about the, in the end, if I write 1 by s plus 1 by t plus 1 by u, we don't know s and t, and you are agnostic to the dimension of this time. So
I see. Okay.
Yeah. So far, I mean, I should say that, although I think not have time to talk about loop amplitudes, but we can generate the integrands for the, for the scalar field theory, like phi to the p through this two positive geometries. And again, but it's an integrand, so it's agnostic about the dimension. But it's scalar because it's scalar. Yeah. So of course, in general, if you want to, if you want to work with fixed spacetime dimension, then we have to go to what are called momentum twisters, where gram determinant condition is satisfied canonically, and so then we can't. I think we can't work with this kinematic space, this Mandelstam space, and it is this momentum twister space in which amplitude was anyway, for the super young Mills was defined. So perhaps even one has to just go there for generic theory. Yeah. But that's open.
Hi, Alok. Since people are asking questions, can I also chip in? Yeah. So it seems like locality in your picture is inbuilt. How is that?
No, locality is not inbuilt. I mean, it will emerge as we will see. Right now, like we don't even have a theory. We don't have a dynamics at all. I mean, we just have this kinematic space, and mathematician told us that from this we can start building some combinatorial objects, and then we will see how locality kind of emerge from there. So far, no.
Oh, I thought you said that you only get polynomial interactions. That's not.
So right. I mean, we will get it eventually, but so far I haven't. I mean, that was I was just looking ahead. Okay. I mean, so far we don't have anything of that sort. Like we are just building it from here.
Okay. Thanks.
Yeah.
Hi, Alok. Can I ask a quick question?
Yes.
So when you say that these Xijs dissect the n-gon,
yes.
So for instance, in the example you have shown, one would also have something like x to 5, right? Or x to 4.
Yes.
So you're saying that it is different subsets of the basis elements which give you different dissections of the n-gon, right?
Yes. I just gave one example here. You are right that of course different Xijs give you different dissections. In fact, that's exactly what we'll exploit to build all these polytopes. So the example I have given here breaks it into triangles, as you see. But you could have you could just take x14, which just breaks it into 2 quadrilaterals, and that will generate as different polytopes. Yeah, exactly. You're right.
Okay, thanks.
So yeah, I think this is related to your question. So I mean, this is the result that mathematicians have developed, actually starting from 60s and till like 2017 in some sense, that basically any dissection generates a combinatorial polytope. So this is the first result in this appeared in 60s, and then the most recent results have appeared in 2015 and after that. And for the purpose of this talk, we will sort of, and this is a little bit related to Rajesh's question also. So we will break this dissection into 2 species. I mean 2 classes. One is what we call pure dissections, where each cell that the n-gon is divided into is the same cell. So either it's a triangle or a quadrilateral or pentagon, but they're the same cells. But in general, we can also have mixed dissection, which where you have 1 triangle and 1 quadrilateral, for example. And all of these dissections generate a class of combinatorial polytopes. So that's what I just want to review now. So let's first look at the oldest known polytope, which came from breaking the n-gon into triangulations. So if you break if you choose dissections which break your n-gon into triangulation, then you get the sort of mother of all of these polytopes, which is called Accordiohedron or Stashev polytope. I mean, Jim Stashev discovered it in his PhD thesis in 60s. And I just give you 2 examples before giving you some properties of this associator, which are really quite striking. So if you take a foregon, then as you can see that you can break it into 2 triangles in 2 ways, and you can go from one dissection to another by just 1 flip of the chord. So 1 3 can flip to 2 4. So this combinatorial polytope is a 1-dimensional polytope where the vertices are the 2 triangulations of the foregon, which I denote as 1 3 and 2 4. And similarly, if you take a pentagon and you break it into triangles, then you get 5 possible triangulations. And these triangulations can be glued together very nicely, and you get the resulting combinatorial object you get is also itself a pentagon. And what the labels I have denoted here are basically labels of the chords. So 1 3 1 4 is chord which tells you what is the triangulation. And the 1,3 label is telling you that the edge of this pentagon is labeled by one dissection, which is common to two triangulations. So there are two triangulations, 1,314, 1,335. And the way we went from 1,314 to 1,335 is by flipping 1,4 to 3,5. So we kept 1,3 fixed. So that edge of this associahedron is labeled by 1,3. So that's the labeling of the edges, and the labeling of the vertices is the complete triangulation. So I mean, it is quite. I mean, these are maybe an example, but what is amazing is that for any n-gon, there is a consistent gluing that you can do like this, and you get a closed polytope, which is called the associahedron. And so let me just give you some property. I mean, these are sometimes mathematicians call them mythical polytope because they're very unusual properties. So, okay, the first is just the dimension. So dimension of this associahedron is same as the number of chords you need to triangulate. So that's n-3. But what is interesting also is that each vertex of an associahedron is always adjacent to precisely n-3 faces. So of course, as you see that in the first example, vertex is adjacent to one-dimensional face, and the second example, each vertex is adjacent to two edges. So the number of edges it is adjacent to is same as the dimension of the associahedron. So this class of polytopes, which are kind of special, are called simple polytopes. So example of a polytope which is not simple is if you just take a triangle with nothing inside, so just a one-dimensional triangle, then it's not simple because the dimension of the triangle is 1, but each vertex is adjacent to two edges. But the property which is most relevant, as we'll see for physics, is that which is the kind of super unusual property, that every boundary of the associahedron, some boundary of say some codimension k, is always a product of two lower dimensional associahedra. So what this means is that if we have drawn here A4, we have drawn here. Sorry, I should have called it A4 and A5. I apologize. I called it A1, A2. But if I look at A3, which I call A6 here, so sorry, I just think of the A1 as A4 because it's a foregone, built from foregone, and A2 as A5. And if you look at face of A6, then you can only get a square, which is a product of two A4s, or a pentagon, which is a product of a pentagon and a point. But you can never get a face which is a hexagon. So, and indeed, you can draw A6 and see that that you will never get a face which is a hexagon. And this property is related to factorization property of amplitudes, as you will see. But of course, this is so far nothing to do with amplitude. It's just some combinatorial property of this polytope. Now, but the same ideas can be used as mathematicians realize, although much later, I think decades later, is that to build polytopes which are coming from much more general dissections, although they are more subtle. So here I just recap the basic property of associahedron in the first line. So the dimension is n-3, and each vertex of the associahedron is in 1-to-1 correspondence with complete triangulations of the n-gon. And if you take a codimension 1 face, which usually called facet, then it is in 1-to-1 correspondence with take one triangulation T and remove one chord, like say Ij. Then you get like a partial triangulation, and each face is in 1-to-1 correspondence with a partial triangulation. And now we can ask, okay, what if instead of triangulations we had say quadrangulation of a polytope? Can we get a polytope? And naively you would guess that you would do something like this. So let's say we have a hexagon, then we can break it into quadrilaterals in 3 ways by 1, 4, 2, 5, 3, 6. But this obviously will not give us any polytope because each edge of this resulting, the polytope is now a triangle, and each edge of this triangle is basically an empty hexagon because the only thing common between 1, 4, and 2, 5 is an empty hexagon. So we have 3 distinct edges, but they are combinatorially the same. So it's not a consistent polytope. It gives something which is kind of nonsense. So this doesn't work, and maybe this is why it took a while for mathematicians to also come up with some a clear definition of this kind of polytopes. And so, here I'll give you first example, and then from there we can see what the definition is. So the idea, this polytopes where the dissection is not through triangulation was developed in a series of papers by Baryshnikov, Shapoton, and Pilot and his collaborators. And the idea is the following. So I just explain through an example. So suppose we take this hexagon 1 to 6 again, and we take a quadrilateral obtained by 1, 4, the chord 1, 4. Then what is important here is to look at the dual hexagon. So the dual hexagon also has 6 vertices, but if you notice, I have only labeled 4 of them, which are adjacent to these red chords. And so in the dual hexagon, the quadrangulation which is adjacent to 1, 4 is only either 1 tilde 4 tilde in this notation or 3 tilde 6 tilde. And so I get a one-dimensional polytope where one vertex is 1 tilde 4 tilde and one vertex is 3 tilde 6 tilde. So unlike the triangulation where starting from the triangulation we get a unique associator, here depending on the choice of the reference, which is 1, 4 in this case, we got this polytope. But of course you can quickly see that if you have chosen your reference to be 3, 6, then the connected dual quadrilaterals are either 2, 5 and 3, 6. So you get a different combinatorial polytope. So for the hexagon, you basically get 3 possible combinatorial polytopes. So already situation is more intricate than the associahedron, where in a given dimension you have a unique polytope, but here your polytope depends on the choice of the reference dissection that you start with. So all the polytopes you obtain from any dissection are collectively called Accordiohedra. That's why this notation AC. But if these are triangulation, then we get this magical polytope, which is the associator. And in other cases, we get polytopes which depend on the reference dissection that we start with. So that's why we club them together, because they are not as neat as the associator. So is there any question about definition, please ask.
So, Alok, I'm sorry, but if you could go over that hexagon example again.
Yes.
It was a little too fast for me.
So this one. Yeah. So here you see that if you look at the dual hexagon, then the edge which is 2, 3. I mean in the dual hexagon, if you look at the vertex 2 tilde and the vertex 5 tilde, they are not adjacent to 1, 4. So that is why I have not colored them.
They're not adjacent to 1, 4.
1, 4. 1, 4. So 1, 4 is the red chord, and the dual vertices which are in the edges next to it are 1 tilde 6 tilde and 3 tilde 4 tilde. But 2 tilde 5 tilde are not touching the. They are not adjacent in that sense to 1, 4.
Okay.
And so now we see that so then the only two. So in the dual hexagon now the 2 quadrangulations which we obtain in this way are 1 tilde 4 tilde and 3 tilde 6 tilde. We do not get 2 tilde 5 tilde because it's not available. It's not adjacent to 1, 4. So it's a definition. And
yeah, I don't understand why it is 1 tilde 4 tilde. Sorry. You're saying that so you form the dual hexagon. So these vertices, you form a hexagon. You haven't shown the one with 5 and with 2, but that's okay. But supposing you imagine drawing a hexagon with all those, then you're saying somehow the edge 1 tilde 4 tilde and 3 tilde 6 tilde, these are ways of dividing the dual hexagon into 2 quadrilaterals, which are allowed.
And we are we are only allowing them. So if you look at the figure below, So if you look at the figure below, you see that if you wanted to go from the edge 1, 2 in the original hexagon, not in the dual, to 4, 5, we can go through a connected path through 1, 4. So we go through. That's what the path that I've drawn here in the Z, in the like inverse Z shape. But if you wanted to go from the edge 2, 3 to 5, 6, there is no way you could go by a connected path involving 1, 4, because they are not adjacent to 1, 4. Is that?
No, I didn't understand what you said last. This zigzag, the Z path.
So you see that if I want to go from the edge 1, 2 to 4, 5. If I want to go from any interior point in the edge 1, 2 to the edge 4, 5, and I want to go through 1, 4, the red chord 1, 4, then there's a connected continuous path I can take, which is this zigzag path. So you go from 2, 1, 1, 4, 4, 5. That's the connected path that I can take.
No, can you? You're saying you go to this thing, then you go along the chord, along the red chord, and then you go.
Exactly.
Okay.
Yes. And similarly, if I want to go from say the 3, 4 edge to 6, 1 edge, I can also go through a path which is connected via 1, 4, which is 3, 4, 4, 1, 1.
Okay.
Yeah.
All right.
But from the other one we don't have, and that is why we do not include. So that is
the other one, because there's no one. The 1/4 path is not. I mean.
Exactly. Yes.
So you're only allowing paths which are through the
The reference dissection, the reference which is the red dissection in the original hexagon.
Okay, so you don't want to go through 1, 3, then 2, 1, and so on. I mean,
Yes, yes, we don't.
3,
Yes,
2, and
yes.
2, 1, and then you go. That you're not considering as an allowed.
Yes, so yeah. So there is a yeah. I should have put, there is a actually I'm giving you an example, but there's a kind of a precise definition, which is that, you know, if you go from the 2 tilde to 5 tilde, and if you look at the if you look at the shortest path here, then it goes through 2 tilde, then it crosses 1, 4, and then it goes to 5 tilde, like just horizontal line in this figure. Now that line is entering the cell. So if you look at the cell 1, 2, 3, 4, that's a quadrilateral. That line is entering the cell at H23, but exiting at the opposite side, which is 1, 4. So that is ruled out. So those paths are ruled out. So that's the part of the definition of an Accordiohedra, that any allowed path in the dual should not enter and exit any cell through opposite sides.
I see. Okay, I think I'm beginning to get it. Yeah, thanks. Sorry to slow you down.
So no, sorry, I should have put, I thought, yeah, I put through example, but maybe it is more confusing. I mean, there is a nice definition, but yeah, which I think, which would have satisfied me much more. Okay, so now let me just give you some slightly more examples. So already you see that Accordiohedra are a bit more intricate, because in a given dimension, we have more than one. Because of the fact that they depend on the choice of the reference. So this is a notation that we will use. So AC superscript n dp. I mean, it looks like a mouthful. It's Accordiohedra where the number of vertices of the so where we have n gone, and where we have a reference dissection which divides the n gone into p cells, which we just call p division. So this is the notation that we are using. So AC n d4 would mean that we divide the n gone into quadrangulation. AC and D3 would just give us an associated. And so I give you two examples where P is 4 and N is 8. And here it's interesting that not only we get more than one polytope, we get two distinct kind of polytopes. So if you start with a reference which is 1, 4, 5, 8, as drawn in the diagram on the left in the inside the square, then the resulting polytope you get through the rule that we're discussing with Rajesh is a square. But if you start with a reference which is 1, 4, 1, 6, then the polytope you get is a pentagon. So not only you get more than one polytope, but you also get different topologies of these polytopes. So it's a quite a rich structure, and it gets more and more complicated this way. But we can, okay, yeah.
Alok, why did we were talking about Accordiohedra, right?
Yes.
So why did we start talking about the Accordiohedra?
No. So yeah, I'm just saying that given the kinematic space, which is a bare structure where each xij basically can be thought of as a chord in a n-gon, just using these chords, we can generate this closed combinatorial polytopes, which is quite interesting. So we cannot, not only do we generate, can we generate Accordiohedra, we can also generate Accordiohedra. I mean, they are all there.
Okay.
And as you will see, they're all sitting inside kinematic space. It's not like up to us. I mean, we just have to find them, but they're sitting there in the kinematic space, as you will see, and they give us the amplitude. So yeah, that's why I just discussed them. So although they are more intricate than Accordiohedra, maybe not as clean, but they can be built in the same way through consistent combinatorial rules as Accordiohedra. So so nothing stops us.
So do Accordiohedra and Accordiohedra exhaust the possibilities?
From dissections, yes. I mean, yes, from dissections, they exhaust all. So all the polytopes you obtain from dissections are called Accordiohedra.
All right, thanks.
Here I'm giving you an example of only, as I said, these pure Accordiohedra where we are breaking the n-gon into cells which have the same valence, but the definition exactly as it is given, what we're discussing with Rajesh also, it is true for any dissection. You can have with any dissection and you can generate a closed polytope. Right? So it's an amazing, in some sense, a remarkable definition that it gives you a closed polytope in any dimension, starting with any reference dissection. Yeah. So yeah, okay. So yeah, so he is just so if we so for Accordiohedra, which is say in terms of, so if I look at quadrilaterals, so I break the n-gon into quadrilateral, then the polytope we get, which is an Accordiohedra where each vertex is in 1-to-1 correspondence with So if I call the reference dissection Q, then each vertex is one-to-one correspondence with not all dissections, but what are Q compatible dissections. So by Q compatible, I just mean, here the dissection compatible with 1, 4 is 3, 6. So we get a polytope where one vertex, so 1, 4 is compatible, 1 tilde 4 tilde is compatible with 1, 4, and 3 tilde 6 tilde is compatible with 1, 4. So the vertices of this polytope are in one-to-one correspondence with all the dissections which are compatible with the 1, 4 dissection in the original hexagon. So that's the definition. And similarly, it's not very important, but the same way for Accordiohedra faces were in one-to-one correspondence with partial triangulations. Here the faces are in one-to-one correspondence with partial dissections where we remove one of the chords, for example. And the dimension of these polytopes is same as the cardinality of the dissection. So if you have, as you see that in this case, if because we have two cardinalities 2 of the dissection, we get a 2-dimensional polytope, and here we got 1-dimensional because we have just one dissection which breaks it into quadrilateral. So yeah, so that's the okay. So that's the, and the number of cardinality of a dissection if P is 4, that is you break the n1 into quadrilateral, is established by Chapoton. It's some commutator thing only, so it's n-4/2. So we get n-4/2 dimensional polytopes, combinatorial polytopes. So for generic n, you see that it is smaller dimensional polytope than Accordiohedra. So Accordiohedra is the biggest actually, because the triangulation has the biggest cardinality among all dissections of an n-gon. So Accordiohedra is the master polytope even in that sense, the biggest polytope, and other ones are like smaller and smaller dimensional polytope. Okay, so here's just some feature. I'm just summarizing them. That for any so for P equal to 3, we got Accordiohedra, and I'm just distinguishing P greater than 3 because this Accordiohedra is not as neat as Accordiohedra. But for each dissection, we get one Accordiohedra, which is just called ACD. And okay, there is some small property which is interesting, that if you take two dissections which are related by just a symmetry, like a dihedral action, then the shapes of the Accordiohedra don't change. So in other words, just to give you an example, if you take reference 1, 4, 1, 6, you get a Accordiohedra which is a pentagon. And if you took the reference which is 3, 8, 3, 6, which is just like a rotation of 1, 4, 1, 6, then you again get a pentagon, but that pentagon will have different labelings of the vertices, but the shape will remain the same. So the shape will only change if you change the combinatories of the dissection. I mean the geometry of the dissection itself. You just rotate it, the shape will. So now, okay. So far we haven't really touched any physics. We just say that okay, just from this bare data we get this interesting combinatorial polytope. But now, of course, we we need to see how this leads us to amplitude. And interesting enough, CHY formalism sort of told us that there is a hidden symmetry of the amplitude that was kind of maybe not appreciated before for a long time. So if you do not know CHY formalism, it is completely okay. But I mean, then you can take this symmetry as a postulate, which is also fine. But if you know, maybe you will appreciate this a bit better. So if you take CHY scattering equations for massless particles, which are written here, and these xij's are this, as Surat was asking, these planar variables, and sij's are just pi dot pj. But of course, we can write Sij in terms of Xij, which is written below. And this is a very mundane symmetry if you think about it. Like if I just take Xij's and just scale them with the same function of all the x's, then of course this equation don't change because it just f just gets scaled out. So it looks like a silly symmetry. Like these equations are invariant under scale symmetry of x's in this sense. But actually, this symmetry turns out to be something which we can exploit to do something quite interesting. So just to continue a little bit with CHY, I apologize, it's a bit of a diversion, but it motivates some of the structure a bit better, because there is a history to this symmetry which comes from dual conformal invariance in amplitude, but that's above my pay grade. So I'm trying to do something which is simpler than that. So in CHY formalism, so there are two inputs we take from CHY. One is that there is this sort of mundane looking symmetry of scattering equations, and the other is that the amplitude in CHY formalism come from integrating some differential forms on some auxiliary space. I mean, what the space is not important, but the role of a amplitude is a function, but that function is sort of predated by a differential form. And so there are these two inputs that we want to use to sort of start building some interesting structures in the kinematic space here using the combinatorial data that we have. So the idea is that, okay, first question we can ask is that, okay, suppose I take this mundane symmetry a bit seriously, this kind of projective invariance where we scale all the x's with the same function. Then can we classify all the forms on kinematic space which are projective in the sense that which are invariant under the scale symmetry? And of course, that is a very hard math question. I do not think the answer is even known. But it turns out that a large class of these forms is parametrized by the Accordiohedra. And so this is why Accordiohedra suddenly become more interesting from physics perspective. So let me just tell you an outline of how we build this form. So the point is that each of the Accordiohedra generates a unique form of rank, which is same as the dimension of the Accordiohedra. And it is projective in this sense that if you scale all the x's with a function f, then that form will not change. So like I just in the first line, I just recall what the kinematic space is just for just the xij's are this pi plus pj minus 1 square. And so I'm going to give you the result because and we will give some example to understand what these forms exactly are. So again, so far these forms don't have anything with any physics or theory, but it's just something which we are kind of building through some combinatorial data and some lessons we learned from CHY. So let's say that, so I'm giving you the first expression, then we will see some examples. So let's say that we take some reference dissection D, and let's say that D tilde is some dissection that we obtain by flipping some of the chords of D. So, like for example, in the n equal to 6 case, 1, 4, 1, 2, 3, 6 by 1 flip. So there is, so the sigma will be 1 basically in that case. Then the idea is that this is the form. So with each Accordiohedra, we define a form which is of this type. So we take all the ij's which are in D tilde, and we just wedge D log of this guy. So it's like D xij by xij. But so there are many terms. I mean, you sum over all these D tildes, and the D tildes which are basically related by odd number of flips with respect to the reference come with a relative minus sign, and the one which are with the even number of flips come with the plus sign. And what is quite interesting is that this form is projective. So this form is invariant under individual term is of course not individual term is okay, but in the end there are cancellations between terms so that you get finally the projective image. So let me give you some maybe example to see what I mean. So if you look at the Accordiohedra example, so in the first example I'm just looking at the one-dimensional Accordiohedra. So I start with the foregone, and it gave me this what we call A4. And now the form we get using this prescription, I mean this formula which was proposed by Arkani Ahmad by Hen Yun is this one. So we get D log x13 and minus D log x24, and minus is because to go from 13 to 24 we needed one flip. And this k is a constant we have not been able to fix yet because this for any k this form is projective, of course. I mean if I scale 1, 3, and 2, 4 with the same function, it doesn't change. So individual term is not projective. If you see, like D log x13 is not projective because the function is not a constant, so it gets differentiated. So but what is striking is that the full thing is projective. So it is in some sense, I mean, spiritually, reminiscent of the BCJ representation, where individual terms are not color kinematics dual, but the full sum has this symmetry, nice symmetry. And in the second line, I've given you example for the Accordiohedra, which we mentioned before, where we have the one-dimensional Accordiohedra with vertices 1, 4, 3, 6, and there again we get a projective form up to a constant normalization constant. So, is there any question at this stage? So far again, no physics, but we could build some interesting structure in the kinematic space from So the postulate, the new postulate we have introduced is the projective invariance, if you want, where we are demanding you to look for forms which have this symmetry, and we are using the combinatorial polytope to generate such forms. I mean, there could be many more such forms, but we get a large class just from this combinatorial polytope.
Sorry, Alok, maybe this is stupid, but the terms that appear in the sum, you're saying it's for corresponds to each vertex, is it? What is it that you're summing over? I didn't quite catch that.
Yes, each vertex, yes. So D tilde is like a complete dissection of the n-gon, and each complete dissection is in 1-to-1, correspondence with the vertex.
Okay, thanks.
So and these forms have interesting property in the sense that they have simple poles at all the faces of the Accordiohedra. I mean, at all the combinatorial faces of Accordiohedra, because you see that the first form, the first line has pole at x13 equal to 0 and x24 equal to 0. So I mean, conceptually, it looks like it has poles at the locations of the vertices of the Accordiohedra. Similarly for the second one, and it has pole nowhere else in the kinematic space. It has only poles at the vertices of the or the boundaries of these polytopes. So it has simple poles at the faces of the Accordiohedra and nowhere else in the kinematic space. So of course, these are things we can prove, but here I just explain through some example. And now this K is so far very arbitrary because we can't fix it from projective invariance. But if we put a normalization condition that residue of this form at each vertex is plus or minus 1, then the overall constant is just plus or minus 1. So up to a sign, we can, by demanding that the residue at any of the vertices of the Accordiohedra becomes plus or minus 1, we can fix this normalization. So let me summarize what we have so far. So for planar, I mean, I shouldn't have said this. I mean, we haven't really looked at amplitudes, but for planar data, planar kinematic space, we see that we went from the Xij variables to chords of a n-gon, and from these chords we generated these combinatorial objects, and then we took some intuition from CHY or some symmetry of the scattering equation, which is this projective invariance, and this combinatorial data to generate a class of forms which we are calling d-log forms, because they are basically they have logarithmic dependence on the x-axis. So far, okay. So far, even now, we don't have any theory or S matrix yet, but this is what we have established in the kinematic space. So we have some geometry now, and we'll see how that gives us amplitude. So if there's any question on this, I can. Also, Naveen, you can tell me if I'm. You can stop me anytime.
Yeah, sure, Alok. Please go on.
Yeah, okay.
We have a lot of time.
Yeah.
So, I mean, we have 7 minutes till 4, but we can, of course.
Okay. Then I'm way. But anyway, yeah,
no, you can take more time. You can take more time. Completely fine.
So,
hello.
Yeah. Yes.
So Accordiohedra are also examples of positive geometries.
Yeah, I haven't defined positive geometry yet. So sorry, I should maybe just say it at this stage. So positive geometry is just any geometry which is such that it has boundary of all 4 dimensions. So in other words, any polytope is a positive geometry, trivially, because it has all possible boundaries from codimension 1 to codimension n. But if you so a classic example of something which is not a positive geometry is a disk, which has a boundary of codimension 1, but it doesn't have any boundary of codimension 2, right? So, but we are, as you can see, we are only getting polytopes, so they are all positive geometries. Yeah, thanks. Yeah, thanks a lot for that. I should have said that. But now in order to go from these forms, which are just some kind of they are forms. Of course, they have nothing to do with amplitude, but because first of all they are forms and they come with this relative minus signs, which we don't expect for scalar field theories amplitude terms to have any relative minus sign. So so we still have some way to go to get the amplitudes of any theory from here. But the missing ingredient is that these polytopes so far that we have, they are combinatorial polytopes. We haven't really geometrically realized them inside the kinematic space. So that is what we have to do. We have to find out a way to realize these polytopes inside the kinematic space. But here we would, it will be like sort of self-defeating if we have to give some input from physics to realize these polytopes. And of course, as you can see, there are infinitely many ways to realize these polytopes in a kinematic space. So just to give you an example, if you take this A4, which is a one-dimensional polytope, and we say that it is located at x1, 3, its 2 vertices are located at 1, 3 equal to 0 and 2, 4 equal to 0. But it can this line segment can have any slope. So it is not it seems like there is no way to choose a particular realization of this one-dimensional associated. Of course, if I have in mind some answer, I could choose some realization, but that would defeat the purpose. So something from the Accordiohedra itself should pick out a realization. I would say this is the most striking part of this program, that somehow there is a canonical realization that mathematics gives you for this, which are relevant for amplitude. I think that's what I will try to explain now. So this is what you want to understand, which is kind of the key point, that are there realizations of this Accordiohedra inside kinematic space, which are generated by in some sense intrinsic properties of the Accordiohedra. Like we shouldn't appeal to some physics principle to find this realization. So I first give you the answer. and then we will see how I mean what was the origin. I mean how it was derived. I mean there are many derivations. I will give you one simplest possible way to understand this answer. So we want to take any of these polytopes which is obtained by some dissection D. At this step, this D can be anything. So it can be a pure dissection or a mixed dissection or anything. And I'm giving you an algorithm how to realize this polytopes inside kinematic space. So given a D, let's consider DC as a dissection which is obtained by just counterclockwise rotating D. So just to give an example, in the line on the left, if D is 1, 3, then DC is just 2, 4. Now you look at the following equation. So we will see how they are derived. I'm just giving you the result for now. That take Sijs. Remember, Sijs are just linear combination of Xijs. And look at these linear equations. That Sijs are equal to minus Cijs for all the ij chords which are not in DC. So which in this case you put S13 equal to minus C13, but that's it. Like only one equation in the case of E4. And you demand that the C's are positive. Now you can immediately check that this will give you the right, at least the right number of equations to give you a realization, because if you just look at the number of equations that we have, that is basically equal to n into n minus 3 by 2 minus d. So I mean it's some algebra, but you can immediately check that if you use these equations and whatever locus you get in the kinematic space, that is the dimension, which is the dimension of the polytope. And so I give you here one example, which is, I mean, two examples, sorry. So if I take the Accordiohedra, one-dimensional Accordiohedra, and I use this equation, Sij equal to minus Cij, so only one equation, which is S13 is minus C13, that translates in the x variable to just this simple equation, which is x13 plus x24 is a positive constant. So you see that out of all possible slopes of the line we could have used, we get like a sort of a symmetric, more symmetric possible realization of this segment. And similarly, if I use these equations, and there are three equations, if your n is 5, then you can see that you get a particular realization of the two-dimensional Accordiohedron. So you got a so just to recall that the two-dimensional Accordiohedron was a pentagon. So we are getting a pentagon, but with very specific slopes, as you can see. So there are either vertical, horizontal lines, and then there is this x24 equal to 0 phase, and that phase actually has a 45-degree line. So it is a very kind of symmetric polytope. But these realizations were obtained, as we will discuss in a moment, not from any physics input. I mean, they were obtained by ABHY conjectured this from some physics ideas, but then they were derived by mathematicians using intrinsic properties of these polytopes. So for Accordiohedra, this particular realization, so when I say realization, I just mean this set of equations, Sij equal to minus Cij for all ij which are not in DC. And for Accordiohedra, this realization was kind of discovered by ABHY. And I think they did use some physics intuition to, I mean, it was completely ingenious construction, but then it was shown by Weiser, Mate, and U. Thomas and all that actually these realizations are the ones you would obtain if you only relied on the intrinsic properties of the Accordiohedra and you just somehow want to build some realization from there. Now, the same idea actually worked, which is fairly striking in the case of Accordiohedra, and this was done by Paluk and Pilod and their collaborators, that you take your reference dissection D and then you put the same set of equations, Sij equal to minus Cij, where ij is not in DC. So here I just give you one example. So let's take a reference dissection which is 1, 4 and 3, 8. So this is not even a pure dissection. It breaks the 8 gone into 2 triangles and 1 quadrilateral. And so this is a bit weird Accordiohedra, but we can get a realization of it in kinematic space just by putting Sij equal to minus Cij, where ij are not 3, 8 and 4, 7. That's it. And we can check that it gives you a convex nice realization of this Accordiohedra. So I'll tell you the way it was derived by mathematicians, which is completely above my pay grade. So I'm just kind of sketching it, but I will then tell you a very beautiful, simpler way to understand this realization. So the approach that just in words, what mathematicians use is that you can start with a triangle. Suppose you're looking at Accordiohedra. So you break your n-gon into triangle. Then each of this triangle gives you a quiver. So I have drawn the quiver on the left in the n-gon, where basically a quiver is, as you can see, that everything which is in the red vertex. So it is starting from, so here the triangulation is 1, 3, 1, 4 up to 1 n minus 1, and it gives you a linear quiver which starts from the vertex on 1, 3 and ends at the vertex 1 n minus 1. And using this linear quiver, one naturally obtains what is called a type A cluster algebra. And these cluster algebra properties were used to precisely produce these ABHY realizations by U. Thomas et al. And then these ideas were extended by Pilot and the collaborators for any dissection. So they showed that, if you start with any dissection which is not a triangulation, you again have a quiver. And even though that quiver doesn't always give you some cluster algebra, it gives you something called a string algebra or path algebra, and that can be used to generate this realization. Okay, so I just keep this. But now let me tell you how to sort of understand these realizations in a much more simple way, which was a really amazing construction of Nimma, Song, and Salvatore and Thomas. And this is an idea that they call the causal diamond construction. So this is I just want to emphasize that this is a way to understand these realizations, but the realizations themselves came from some math properties. So we have the realizations, now we are just trying to understand them from some simple ideas. Yeah. So just to remind you that these x variables are, they have these two kind of property that x1n is 0 and xi minus plus 1 is 0. And based on these properties, what Nimma and all showed is that there is an interesting null lattice that you can span, which is labeled by xij. So let me just show you what that is. So, it's a completely abstract lattice, as you can see, where, if you basically every vertex is a xij or a ij variable, and the boundary of this sort of so this null lattice is bounded because x34 is 0, x45 is 0. So all the two vertical sides are basically where x goes to 0. And the reason this is interesting, this is an interesting structure, is that if you take if you look at the diagram on the left, so both of these are called, by the way, causal diamonds. And if you take the diagram on the left and look at 3, 6, which is the vertex which is sitting at the intersection of all the shaded regions, then all the diagonals that cross 3, 6, in the hexagon, they are strictly inside the light cone. So for example, 2, 5 crosses 3, 6, so it's inside the light cone. But 2, 6 doesn't cross 3, 6, so it's in the null direction as compared to 3, 6. And similarly, if you look at anything which is space-like related to 3, 6, for example, in the diagram on the right, 3, 5 doesn't cross 2, 6, and it's space-like related to 2, 6. So there is an interesting, so this quote-unquote causal properties, I mean, these are causal in the sense of just some abstract causal properties, also are related to that, like the intersection of chords, in this dissection. And one interesting thing is that if you take any null slice, that gives you a triangulation, which is kind of easy to see, right? Because if you just look at the diagram on the left, and you see there's a null slice which is 3, 4, 3, 5, 3, 6, 3, 1, and 3, 2. 3, 4, 3, 2 are of course 0, and we get 3 chords which are 3, 5, 3, 6, 3, 1, which triangulate the hexagon. So any null slice will give you a triangulation. So these abstract objects are what they call causal diamonds, and you will see that these are simplest way to understand these cluster algebra realizations of the Accordiohedra. So I give you just one example. So let's take, of course, but these are redundant. In some sense, these are redundant diamonds because every chord is repeated many times. Because what is happening is that if you move in time-like direction, then as you can see that 3, 6 evolves to 4, 1, then 2, 5, then it will go back to 3, 6. So the whole thing has some periodicity. And so what we have to work with is a domain where every ij is occurring only once. And these domains are called fundamental domains. So I give you one example here of a fundamental domain for n equal to 5. So we have it's a pentagon here. So we know that the corresponding associahedron is a 2-dimensional polytope. So the fundamental domain that I've drawn here, of course, there's no unique fundamental domain. You can pick any. So I've just picked one here. And now you see that in this fundamental domain, there are three wedges, like three smallest wedges, which are not intersecting. And for each wedge, these cluster algebra equations take a very beautifully simple form. So you see that if I take the red lattice, then it gives me an equation which is x13 plus, so the equation that we can write from this lattice is, if you evolve once, then you basically put a plus sign. So x13 plus x24, it's like a Gauss law. So x13 plus x24 minus x14 minus x23 is a constant. So it's literally a discrete version of a Gauss law, because and so you get three equations. All the three equations I have written here in the equations adjacent. So we basically get 3 equations, which will give us precisely the realization that, or the equation that we obtain from Sij equal to minus Cij. So I just explain it here, that these equations are the same equations as Sij equal to minus Cij. If you started with T, which is 1353, which is interesting because you see the initial slice in this fundamental domain is a triangulation which is 1353. So it tells you which of the realizations that mathematicians gave us will come once you stick to one fundamental domain. Okay, and just one small aside, I am focused right now on Accordiohedra just for just because of lack of time, but this perspective can be applied to even obtain the the string algebra realizations of Accordiohedra. Although we don't have a solid proof, we work out many examples, so it's some unpublished work that we did. Okay, now finally we have all this setup. So we have 3 things. We have the combinatorial polytopes. We now found them in the kinematic space, and we have the scattering forms which we obtained from combinatorial data and projective invariance. And now it's let me just first give you the answer and then see how it works out. So if you take these forms and you just restrict them to this polytope. So for example, in the first line, I take a form which we obtained from triangulation, and we just restrict it to the Accordiohedra which we have found in the kinematic space. Then it turns out that whatever form we obtain is nothing but a particular function times just a wedges of the d-axis over the triangulation, and this particular function is precisely the planar amplitude in the biadjoint phi cube theory. So so this is where we build amplitude from this from the polytopes. And similarly, in the second line, I've written the same kind of result that we obtained for Accordiohedra, where it is much more subtle now. So what happens is that if you look at one of these Accordiohedra polytopes, which are obtained from a reference dissection set dp, and we again do the same machinery, we have a convex realization, and we have the form, and we restrict the form. Then we get an amplitude, but that's not an amplitude for the planar. That's not a planar amplitude inside the P theory, in the sense that the ordering, the 2 color ordering are not the same, but there is a specific ordering which I haven't written here because it depends on the dp. So one side of the one color ordering is 1 to n, then the other color ordering is some other color ordering, and that's the amplitude we will obtain. So it's again an amplitude in a biadjoint theory for the P interaction, but it's not a planar amplitude in the case of the Accordiohedra. So so just to give you an example for the second case, because it looks a bit weird, that if you take the ordering for the first color index to be 1 to 6, and for the second color index to be 1, 2, 3, 4, 6, 5, then whatever amplitude you get is precisely the form for the for the one-dimensional Accordiohedra restricted to the convex realization. So this is an interesting, I mean, I would say quite a striking result of this program, that every canonical form we obtained from the Accordiohedra gave us at least some color amplitude for some theory. So so the main thing we used here was projective invariance. That was the principle that we used from which came from CHY.
Sorry.
Maybe I stop here and yeah.
So did you mean to say in the previous slide that there is some Accordiohedron for which sigma is also identity, or?
No, I will come to that. I was about to come. There is there is no single Accordiohedra, but we will see for sigma equal to identity how we obtain that, how we obtain the amplitude.
So only some sigma. I mean, if you just go over the space of all the Accordiohedra, you only get some sigma, some subset of the sigma.
Exactly. You get subset of sigma, but you will never get, if it is not an Accordiohedra, you will never get sigma equal to identity for if you take a single Accordiohedra.
Okay, thanks.
I mean, one reason is that because we are starting with the reference dissection, so we are always only taking into account some dissections. And each dissection corresponds to some channels. So we are always missing some channels. So that's I mean, roughly that's the reason we will never recover.
I see.
Okay, so now this is exactly the question that Rajesh was asking. But how do we obtain the amplitude which we are calling planar, which are this, where sigma is identity in this phi to the P theories? And for this, it turns out that the single Accordiohedra does not suffice. But what one can prove is that there is a specific linear combination of these forms where you have to weight, where the linear coefficients are some weights that you have to put, and such that, so there is always some alphas such that you get the planar amplitude in phi to the p theory. But here comes a catch that these alphas are not fixed intrinsically from the positive geometry or from the Accordiohedra. So the only way we fix alphas is to say, okay, we want amplitude. So we know that residue of each channel has to be plus or minus, 1. And so that can be used to, fix these alphas. I mean, what it is impressive that this alpha can be fixed, uniquely determined, and there are super impressive works, I would say, starting from Prashant's work in 2019 to many other works where people have for different class of Accordiohedra, fixed these, using combinatorial properties of Accordiohedra, fix these alphas. But I just want to emphasize that these are not fixed intrinsically. It is something that we fix using the fact that we want the amplitude. So this is one place where somehow the program itself requires some extra input from physics. So now, but we can ask now, okay, why does this work? I mean, at least for say phi cube theory, we really didn't have to use anything in some sense external, except the fact that we had this new symmetry which we discovered from CHY. And in some sense, the intuitive reason is kind of obvious, that because we know that every dissection is dual to a planar Feynman diagram. So for example, like a triangulation 1,3 of a foregone is dual to a diagram which I have drawn there. And so, okay, we know that we started this polytope, it must have something to do with amplitude, but it is still a long way to go from that combinatorial connection of dual of Feynman diagram and dissection to what we have got so far. And the sort of the two key reasons this work is because of this amazing properties of Accordiohedra, or in general this Accordiohedra, where, as we discussed in the Accordiohedra case, I didn't emphasize it so much for the Accordiohedra, that every phase of any dimension of the Accordiohedra is always a product of two Accordiohedras of lower dimension. And this is, it is this reason that basically tells you that when we take these restricted forms of this type, the resulting the amplitudes we get are unitary, because every time we go on shell, it breaks into product of two amplitudes. And the fact that there's a property, sorry, I did not have time to explain, that if you look at this form and restrict to any phase, so every phase, remember, has a pole, simple pole, as we discussed for this form. So if you evaluate the residue of the form on any phase, it always breaks into the lower forms of these two Accordiohedra. So remember that every phase is a product of two Accordiohedra, and that kind of tells you that you have a sort of a nice locality, because there is a simple pole, and that simple pole in the amplitude basically comes from the fact that tree-level amplitude, it is a manifestation of locality. So this is the very roughly, I mean, I haven't done justice to this, but it is this reason we got something which was unitary and local from these polytopes. So this is what we have so far, that we went from polytopes to a class of amplitudes, and as Rajesh was emphasizing before, we have really looked at like phi to the p amplitudes for a single scalar phi. This can be generalized to polynomial interactions by summing over many polytopes. I won't go into that now, but we can ask a more maybe I would like to ask, I don't know if I have time, but a different question, that can we now go the other way? Like, okay, let's take some theory which is a bit more complicated, and is there a positive geometry for any theory, like say any scalar theory that we have in mind? So, for example, the simplest non-trivial example we could think of is we have two fields, phi 1 and phi 2, and we have this mixed interaction, and let's say the phi 2 has a mass. And we want to study planar amplitudes in these theories where all the external particles are, say, still massless. So this is only for simplification, that's not a serious restriction. But of course, it's still an interesting question whether these amplitudes can be generated from positive geometry or from this polytope. So I don't know, Naveen, how much time I have, you have to tell me. I can.
Maybe 15 more minutes. We can just make it around 1.5 hours then.
Oh, okay, thanks. Yeah. Sorry, it took too long.
No.
Okay. So, but we are going to kind of go step by step. So, of course, what we would like to do is for endpoint amplitude, we want to get exact amplitude. But maybe let's start let's start the simplest question, that let's try to build this amplitude perturbatively in lambda 2. So, so for example, we can ask the following question: that are there positive polytopes such that the same thing we did in the earlier part of the talk can be done, so that the polytope generate amplitude for this theory up to order lambda 2 square. That is, we want to look at amplitudes which have only one massive propagator and all the other ones are massless propagators with this interaction that I have written here. So let's try to see if these kind of amplitudes can be obtained from polytopes? I mean, are there any polytopes in the kinematic space which generate this amplitude? So again, here it turns out that somehow now the sort of the physics insights that we had, this causal diamond kind of derivations, help us in defining even the combinatorial polytope. So right now we actually don't have any match thing to go with, because we have two species of fields. So our dissections are not, some dissections correspond to massless propagators, some to massive propagators. So we have two, in some sense, two colored dissection, which correspond to Xij being massless, one where it could be massive. And so it turns out that there was no math literature we had to go by, but there's something that we realized which was quite nice, that let's just look at this fundamental domain that we had, and let's say that we take some of these vertices to be, let's just put them as red. I mean, you should keep in mind this red is massive, but right now we are not using any massiveness. But let's say we have two colored vertices in the fundamental domain, and so let's say 1, 3 is red, and we put a mutation, I mean the flip rule, that a red vertex always flips to a red vertex. Let's just say we put that. Then of course combinatorially we still get the accordiohedron because nothing has changed, but some of these edges become now different color. So we get this from this fundamental domain, we got a new combinatorial polytope, which is what, I mean, we just called it colored accordiohedron, which is what is denoted here. And but this fundamental domain has a, I mean, we started with one chord which is red, which is 1, 3. So of course, every time you, okay, let me give another example. So for example, let's look at this domain, where n is equal to 6. And we start with a domain where 3, 6 is red. So we start with the initial slice in the causal diamond where 3, 6 is red, and we follow a rule. So the red vertex goes to red, and so we get colored 3-dimensional accordiohedra where 3, 6, 1, 4, and 2, 5 facets are red. Every other facet is black. And so it turns out that if we look at, so this rule gives us a class of interesting polytopes, which we call colored accordiohedra, and it is such that if you look at the in the fundamental domain, if you start with the vertex ij, which is red, so when I say we start means in the initial slice, which in this case is 1, 3, 3, 6, 3, 5, ij is 3, 6. So if you start with ij, which is red, then you will only get those ij's which are, I mean, so up to from ij to I plus mod j minus y and j plus mod j minus I will be red. And you can easily check, this is very easy to see, that if j minus I is less than or equal to n by 2, n being the number of, the number of particles, then this colored polytope will have no adjacent red faces. So maybe I can just explain it in this example. So if I had taken in the initial size 3, 5 to be red, then you can see that 3, 5 will go to 4, 6, then it will go to 1, 5. And 1, 5 and 3, 5 will be red, but 1, 5 is adjacent to 3, 5. They don't intersect. Then you would have got adjacent red faces. So so even if you want to look at like very restricted class of polytopes which have no adjacent red faces, you can restrict yourself to choice of initial triangulation where there's only one red vertex first of all, and that one is always at j minus I less than n by 2. So the reason we are only looking at this non-adjacent colored accordiohedra is because we want to compute amplitude, as we'll see, up to order lambda 2 square. So if you want to go to higher order, we have to look at more complicated accordiohedra, but I won't have time to, I think, discuss this. So right now my goal is to show you that there are polytopes which generate these amplitudes in this theory up to order lambda 2 square. So I'm just giving you that those class of polytopes which I'm drawing here. But of course there are many now, unlike the uncolored accordiohedra where for each n there was only one accordiohedron. Now there are many accordiohedra, right? Because every time I start with a given red ij, I get an accordiohedra. So just to give an example, even if n was 5, there are 6 colored accordiohedra where you start with 1, 3 as a red dissection, or 2, 4 as a red dissection, all the way to 2, 5, or you start with 3, 6 as a red dissection. So we can just see it here that if you start with 1, 3 as red, then 1, 3, 2, 4 are red in the polytope. But if you start with 2, 4 as red, then 2, 4, 3, 5 will be red. That way you can go 5. There are 5 of those accordiohedra. And if you start with 3, 5 red, then 3, 5, 1, 4, 2, 5 are red. But that is only one, because if you start with 1, 4 also red, then 1, 4, 2, 5 and there's a typo, sorry, then 3, 5 will remain red. So basically there are six colored accordiohedra that you obtain this way. And now it turns out that okay, so now we want to ask, okay, these are combinatorial associated. So we want to ask, are there realizations of these which generate amplitudes for us for the theory that we have in mind, which is this mixed scalar theory? And now we don't have any math literature to go by, because these colored associated are not tied to any quiver or any so far there have not been any cluster algebra or anything associated to it. So we have to sort of see is there any realization that we can find for these guys without appealing to any math math literature. And it turns out it's quite similar to what we have earlier. So the previous analysis almost works, but with one interesting caveat. So let me define Xij. Now we have two species of Xijs, remember, because my Ij can be red or black. So I'm going to call Xij R if Ij is red, and I'm just going to call it Xij as before if Ij is black. And then it turns out that, okay, starting with this colored associated, we can immediately define a scattering form with the same formula we had before. So no difference. Just that Xij, I'm going to replace Xij with X bar Ij, where X bar Ij can be. So far, I do not know at this stage what X bar Ij really is. It's just that it is, I'm labeling it in two different ways. I'm calling it XRij if Ij is red, and black if Xij if Ij is black. Now, suppose we say that let's look at the same algorithm, which is that we want to realize the associated. So I use the same class of equation, which is Sij equal to minus Cij for Ij's which are not in the counterclockwise reference dissection, but where every X is now replaced by X bar. So so my S bar Ij is the same expression in terms of Xij, but instead of Xij now I have X bar Ij. And okay, so this the first equations are what I just said earlier. And now it turns out that if we can show, because we are going backward, we are trying to find realizations which give us amplitude, and we can show that if this XRij is such that it is given by lambda1 square by lambda2 square times Xij minus m square. So m is coming from the pole, and the lambda to lambda1 ratio is coming from the coupling. Then it turns out that the form we have, which is this form, restricted to the colored associahedra A and Fij, we start generating some terms in the amplitude. It will not generate each domain will not generate full amplitude, but it start generating some terms in the amplitude, and in the end it will generate the full amplitude. So but the interesting thing is that the realization we obtain now is not, it's the slope of all the faces is not just the normals are not just discrete, because as you can see that with this labeling of XRij, you can check that X25 has this linear combination. So you can immediately see that if m was 0 and lambda1 and lambda2 were equal, then this equation will be X25 equal to X35 minus X13. And so that's the equation where all the linear, all the coefficients are either plus minus 1 or 0. But with this coupling, independent couplings, we get the X25 equal to 0 edge has a non-trivial slope, which is neither, which is not just coming from discrete data like plus minus 1 and 0. So this is kind of telling you how, where the continuum of coupling would feature in the polytopes. Because, you would need these realizations to capture the amplitude. And so we just call this deformed ABHY realization. I mean, because, the equations are same as what Nima and Song and other proposed, but we had to do this specific deformation. And then what we showed was the following. Oops. Sorry, I think I forgot I had a formal expression which I think I have not written, that there is a specific way to sum for all the Fij's which give us the full amplitude up to order lambda2 square. Okay, but now let me, I don't know, Naveen, if I have time, I can tell, in 5 minutes, I can tell something about how
yes,
there is a time.
Yeah, definitely. Yeah.
So now we can have the following question that, okay, if I take this colored associahedra and suppose I want to do some kind of an effective field theory analysis. So I take the mass of this phi to field to infinity. What happens to these polytopes? And so I have just drawn here pictorially what happens. So here I have drawn one of these colored associahedra where the massive faces, massive propagators are at x14 equal to m square and x35 equal to m square. And now it turns out that if you take m to infinity, then there are two different, it's basically like you are viewing this polytope running over to infinity, but you can view it from several different directions. And it turns out that if you view it from, if you restrict the region, if you look at this polytope in the M going to infinity from a region which is close to x14 equal to 0. So you are in a region where x14 is much less than m square. Then you get this orange shaded one-dimensional Accordiohedra. And if you are in the x3 phi much less than m square, then you get a this green shaded one-dimensional Accordiohedra. And okay. So, and it turns out that this resulting Accordiohedra we obtain. So you see we are obtaining two Accordiohedra which are both one-dimensional, and this resulting Accordiohedra actually compute amplitude in the theory, which is where you have integrated out the massive field, and so it's a theory which has a phi cube and a phi 4 coupling. So it's a mixed coupling. So one vertex is phi cube, say, and one is phi 4, and the G is the coupling that you obtain. You have to of course take lambda 2 to infinity so that the ratio remains finite. So maybe, sorry, I went a bit fast because I was going over time, but let me just summarize that what we obtained so far for this for these massive theories, that we have as many Accordiohedra or colored associahedra as the number of red dissections that you start in your reference dissection, or the number of fundamental domains Fij. Remember, each Fij was characterized by one Ij vertex which was red in the initial slide. And so here's a formal result actually that we could prove, that if you start with the associahedra which is the which we call an minus 3 Fij, so it's a convex realization of an associahedra, and now you view it, you take the pq face, and you look at the region where xpq is much less than m square. So look at the pq face of this associahedra, sorry, and look at a parallel region where xpq is much less than m square. Then it precisely produces for you Accordiohedra for this theory, the phi cube plus phi 4 theory. So it kind of tells you why, how you get this lower dimensional Accordiohedra from the associahedra through kind of effect, very primitive effective behavior. Okay, so this is one picture that so here I've written the formal statement that if you take xpq much less than m square, I get an Accordiohedra which is defined by a reference dissection which I call dpq. So let me just explain what dpq is. So dpq is nothing but a dissection you obtain by erasing pq. So in other words, if you start with, maybe we can just look at the right hand side of the figure. If you start with a reference triangulation 1 3 1 4, where 1 4 is red, and now I have a colored associahedra, and I look at the region where x14 is much less than m square, then the resulting Accordiohedra obtained is the one where the reference dissection is just this 1 3. So it's a dissection which breaks your a Figon into a triangle and a quadrilateral. And so of course, as you can imagine, that this dissection is dual to a Feynman diagram, which is one cubic vertex and one quartic vertex, which is precisely what you would obtain, expect from this class of theories to leading order in lambda. So for all the analysis into leading order. Okay, maybe I should just stop here. So this was this is the main result, the last bullet point, that at least we have some understanding of how to obtain these Accordiohedra, which are maybe not as nice from associahedra. But we have to look at associahedra which are not somehow maybe discovered by mathematicians yet. They have some colorings which are more intricate. So maybe I stop here. So I'm really sorry going super over time.
No, it was great. Thank you, Alok. Let's all thank Alok by unmuting ourselves.
Thank you.
Thank you for a great talk. So if there are any questions, please unmute yourselves and feel free to ask them.
Hello, sir.
Hello.
Yeah, sir. So we have a halohedron for the one loop label associahedra, right?
But no, actually now that sorry, I didn't have time to go into one loop. Yeah, there's a lot more interesting story in one loop, but I think halohedron is not now the right polytope. I mean, there are these type D cluster polytopes and their avatars which are now more. Yeah, but there is a polytope, if that's what you're asking. Yes, there is a polytope for one loop. In fact, not just for phi cube. Actually, even for one loop phi to the p integrand, with Mrunmayee, we discovered some polytopes that are called, we just call them pseudo Accordiohedra, which give us the integrand for one loop phi to the p for a single massless phi to the p theory. So yeah, there is some progress. Yeah.
Yeah. So how to get the amplitude out of the integrands from those polytopes? So let's say we have that variable L. So how to get the actual amplitude out of those integrands?
So that we just have to integrate. So I think you're asking what is the geometric meaning of that integration over the loop momenta,
yes.
right?
Yes.
I think so too. I mean, so okay, maybe I have to step back a little bit. So in the n equal to 4 super Yang-Mills, the amplitude which was obtained gave us the amplitude, not the integrand. So somehow the it was later realized that the integrand also has a mathematical or geometric interpretation, but initially it was the full integrated amplitude which had a geometric interpretation. So, and that interpretation was that there was the polytope in some auxiliary space whose volume gave us the amplitude, the integrated amplitude. So
yeah,
I think Nima Song could answer this much more. That I mean, the expectation is that for the scalar field theory also that should be a understanding of the integrated object as a geometric thing, but I do not think, to the best of my knowledge, that is known yet. So what we understand geometrically is for the integrand, because they have higher divergences. We have to regularize. We have to go to 4 minus epsilon dimensions if we are in 4 dimensions. So I think it will be more subtle. Yeah, okay. At least I do not know if there's any in the scalar field theory case any clear understanding of the integrated amplitude as a geometric object. Yeah.
Okay, sir. Thank you.
There were a couple of raised hands earlier, but I didn't see them. I think Deepak Vaid had a question.
So Alok. Doesn't Nima say that the amplitude, the integrated version, is proportional to the volume of the amplitude, or is that just
for the amplitude? Yes, not for the. I mean, I think there is a progress. There is certainly a progress they have made using this new class of polytopes that he calls clusterohedra, but I think that is not released yet. So I think there is an understanding of the integral amplitude even in scalar field theory, but I don't know exactly what it is because I think it has still to come out that there was. But the established work which is out right now, we only have the geometric understanding of the integrands. The amplitude. For the amplitude, I think I'm just saying that, not for the scalar non-supersymmetric.
Right. Okay. Thanks. And also, I just want to make one observation here. I mean, it's not really a question. Is something I found very recently is that the associahedron also appears in one of Kitaya's papers from 2006. And he notes that when you look at the algebraic theory of anions, and you consider a fusion category, then the associahedron arises as a statement of something known as Mac-Lane's coherence theorem. Mm-hmm. So it's present not just in
No, I mean associahedra of course also appeared in physics. I think older papers of Moore and Cyber. I don't know if Rajesh or Sujay here. I think these rational conformal field theory papers, of course, as combinatorial object, they occur in many places. In conformal field theory also, I think they have. If you look at Rebo's review, there is a associahedra understanding of some of the crossing these functions, B functions or something. Yeah, I think they have occurred in many places in physics over the years. I agree. Not just in amplitude.
I think Anindo also had a question.
Okay.
Right?
No, that was long time back. Long time back.
I see. Okay.
But since you gave me the opportunity, let me just ask you anyway, Alok. Yes. These interactions that you were talking about, I got the impression that. So can you just explain why phi cubed was somehow singled out, and would it be possible to consider, say, non-renormalizable interactions like, say, many derivatives acting on phi cubed?
Yeah, I think that the derivative interactions is what is not is, at least I feel is open, because somehow the all the forms we get from the polytopes are forms which are this D log form. So in the end, the amplitudes they generate do not have any non-trivial numerator factors. so it's not clear how the derivative interactions, at least right now. I mean, it's an open problem. I think that how do we include derivative interactions in this class of theory? But what is also not at least not completely clear is that if you take I think this was initially Rajesh was saying, suppose we take n fields and with different masses, and we just take even take say just cubic interaction, like between different fields, and you want to compute the tree-level amplitude, like even that, like what I did was up to lambda2 square, and now we have been able to make some progress to arbitrary order in lambda2, but only for examples of like 8 particles, 10 particles. We don't have a theorem for n particles even now, for like if you go to higher order in lambda. So even without derivative coupling, I think lot remain, I feel, to be understood with different masses. And yeah, but it is interesting that these polytopes do exist even when you start including masses, because if I ask from CHY perspective, like I just ask the same question. I have this interaction lambda1 phi1 cube plus lambda2 phi1 square phi2, and is there a CHY formula up to lambda2 square? And it is, I don't think it's completely understood, and whatever little assumption is extremely messy. It's like a very messy formula, whereas here it just comes out from the same geometry, underlying geometry we had before. So in that sense, it's yeah.
So can you just tell me, or maybe for the benefit of the remaining people in the audience also, the 2 sentences about what is the big goal behind this? Is it to sort of replace everything in say scattering by geometry, and then let unitarity, locality, and all these fundamental principles that we are familiar with emerge, become emergent concepts?
Yeah.
Or
I think at least one. I mean, one. So I think one big goal, the way I see it is that the if you take all the developments we saw from recursion to CHY to the color kinematics duality, and one prototype model where they all sort of manifest themselves with this bi-adjoint phi cube theory. And but it was never clear why CHY is a very different formulation. BCJ is a very different formulation. It was never clear, is there a way we can explain all of them together, like BCFW, I mean, in the sense recursion, CHY, and the color kinematics duality of the bi-adjoint scalar. And at least that one thing Associated for sure did, that for bi-adjoint scalar phi cube, explain all of them for the tree-level amplitude. It explained why CHY worked, because it proved CHY formula. I didn't have time to go through it, but for the phi cube theory, it proved the CHY formula. It told you why. Because the world sheet is, that's also associated, and so there was a diffeomorphism between the world sheet associated and this one, and then it basically proved that the form that you get, which is diffeomorphic to this scattering form, is precisely the CHY integrand. So in that sense, it proved CHY. And then if you look at these DXs, like the DXIJs, they satisfy Jacobi identity. So if you replace the DXs with like color, I mean, so there's a color kinematics duality at the level of these forms. And the recursion comes from the fact that, so I didn't have time, but I analyzed these amplitudes as forms, but there is a equivalent way that we can look at once we have this convex realization of these polytopes, there are convex realization of what are called dual polytopes. And the scattering amplitude is nothing but volume of the dual polytope. And now once we have that picture, then we can ask recursion is nothing but building the volume in terms of smaller chunks of volume. So it gives you a nice geometric picture for the recursion also. And so that was one thing that kind of, to unify all this into like a single framework, where the principle that kind of drove was projectivity. But
how
I agree
important was unitarity in this story? I mean,
it emerged. It emerged. It emerged from the fact that we have this. From the fact that the Associated have this property that any face of Associated is a product of low-dimensional Associated. So the fact that when you go on shell, the amplitude breaks into 2 sub-amplitudes just came from the property of that Associahedron, combinatorial property of Associahedron. Which is reminiscent of how kind of unitarity emerged in CHY, right, where the moduli space break into lower dimensional moduli. But here, what is interesting, I think, is that if you look at phi to the p theories in CHY, their integrals are very, very ugly, and they don't seem to have anything to do with phi cube integrants. We can cook them up, but they don't have any geometric interpretation in CHY for the phi to the p. Whereas here, for all of these, they have the same geometric interpretation. We have this family of Accordiohedra, and we have these projective forms, and they gave us amplitude for the phi to the p theory. So, this big question that how do we classify space of all functions in kinematic space, which so I mean that's a very big open question, but in some sense, we are, as a dream that maybe it all comes from looking at all possible polytopes in kinematic space and which admit forms. I don't. I'm just saying that.
Okay.
Yeah.
Okay. Yeah. Okay.
So this last work I say is kind of in that direction, like so because if you could find one reasonable theory for which there is no polytope, then we would question the program, right? I mean, so at least we were happy that for this small case we found some polytope. Yeah.
Right. Thank you. Thank you.
Thanks.
So, Alok, a general question again related to what you were just saying. I mean, for gauge theories and gravity and so on, there's a similar CHY formulas and all that. But in some ways, the kinematics is much more transparent in these twistor variables. Or,
Exactly.
So, what is the connection? Is there a connection between?
Yeah, I think. I think that this. So, I think for a non-supersymmetric just Yang-Mills where we CHY so like nicely understood, I do not think we know any positive geometry yet in any space, whether in spinor helicity space or we do not yet know of a positive. We know a form in the spinor helicity space. Song wrote down a form few aspects. So he took the CHY form and like basically pushed it forward using scattering equations. So he got it is also this D log form where the argument of the log is in terms of spinor helicity variable. But whether that's a form associated to a polytope is, I think, not yet known actually. So that is still I would say, but there has been some work, but it is in maybe in supersymmetric again domain only. There is something called gravitohedron by Trunka where he's looking at I think, but their amplitudes may be in supergravity, which also come from some polytopes. But without supersymmetry, I am not. No, I don't think there's been any. I mean, I have not seen any work. I think that's one of the major open questions. Like even QED, just scalar QED. I don't know how if there is a polytope.
Right. No, I mean the supersymmetry, while it may be useful, but I mean for tree level amplitudes, it doesn't really meaning in the sense
that doesn't matter.
Do it for n equal to 4, you can get the ordinary angles amplitudes also.
I see. So maybe that at least that is definitely one way to see it from amplituhedron you are saying. But the yes, you're right. But the form Song wrote down, which is this by just pushing forward CHY. To the best of my understanding, that form is not associated to any positive geometry. That is maybe one interesting open. But so, we expect that to not live here, of course, as you are saying. It should live in twisters or spinor helicity.
Yeah, it will be in a slightly different space.
Yes, that's for sure.
Yeah. Okay, and just another small question. The mass deformation, if you think of that as also a kind of a quadratic vertex, I mean, as a perturbation, and a quadratic vertex, does that have then a simple geometric, it's not like triangulation, almost like...
Actually, we thought about this. We do not have a good understanding because the way we did it, we really just work with these variables, x13 minus m square as I've written here. And, so we kind of, you're right. We don't know how we thought a little bit about this, but didn't really see how to generate it.
Like a two-sided, a face with two edges. I mean,
that's an interesting point. I don't know I don't know the answer to that.
Whether there's a association.
For sure. Yes, exactly.
It's not triangulations, quadrangulations, but also you include these things.
Something which has just two, right? Some.
Yeah. 1 second. Okay. All right. Thanks.
Thanks.
So, are there any more questions for Alok?
Hi, sir.
Hi.
So I just wanted to ask, what is the inference that comes out that we can express the amplitudes in terms of geometrical objects? So what does that mean in exact sense?
No, I mean, I mean, it gives you a new perspective on how to see amplitude. Like for example, before we did not think of amplitudes as forms, and so now that's definitely a new realization that, and it gives you at least a very bare bone classification that if you look at forms which are these D log forms, then they give you amplitude. So there was this big question in analytic S matrix that what are the class of functions which qualifies S matrix of a unitary local quantum field theory. Okay, we are far away from answering that question, but we see that at least one class of forms, not functions, which do generate amplitudes of such theories are D log forms coming from polytopes. So we are learning something new about definitely already at this stage. I mean, this is a relatively like new program in that sense, because of course the amplitude work is very much old and much more advanced, but scalar stuff is like 4 years. So right now it is really giving a new perspective, like what we discussed earlier, that there are these disparate developments, CHY, color kinematics, and like at least for bi-adjoint phi cube, we can understand all of them from polytope picture, which is quite I find quite nice.
Yeah. Okay. Thanks.
Yeah. I should just say one more thing, that even for all the I didn't have time, that in the as we were discussing with just Anindya also sometime back, that there is a way to like break this dual polytopes into volume and compute amplitude, tree-level amplitude, of course, of these theories from this volume. And it turns out that even for bi-adjoint phi cube, you may be surprised, but there is a simpler, more efficient computation for endpoint amplitude tree level than Feynman diagram, which comes from a different triangle. So Feynman diagram is like one breaking of the polytopes into smaller polytopes, but there is a much more efficient breaking, which is giving you a representation which is non-Feynman diagram, which is efficient, more efficient. I mean, so if you wanted to compute efficient amplitudes tree level for phi cube, then even for that, this one turns out to have a nice use.
Thanks.
Can I ask one last question?
Yeah.
So yeah, you must be quite tired from speaking, but
no, it's fine.
Well, so all of these polytopes, Accordiohedra, Accordiohedra, these are all in 2 dimensions, right? They're just like
no. They are in any They are in so the dimension of the polytope is same as cardinality of the dissection. So if you take an n-gon and you look at the triangulation, so cardinality is n-3, like you need n-3 chords. So the dimension of the associator is n-3. I was just showing because just a drawing was easy for to do, but they are in all dimensions. So the dimension scales in some sense with n, right? N being the number of particles. Yes.
Right. So if you say that your associahedron, let's say, is do you have an associahedron that corresponds to, like, say, a tetrahedron?
No. We so in the 3 dimension there's a unique association. Remember, in every dimension there's a unique associahedra. So there is an associahedra in 3D which has I think 14 faces and some vertices. Okay. And it's not it's a bit more complicated. Okay. But it is drawn. If you look at Nema's paper, they have plotted it. Yeah.
All right. Thanks.
All right. There are no more questions. Let's thank Alok again.
Thanks a lot
for a great talk. Right.
Thanks, Naveen.
Yeah. Okay. So I'll end the. Yeah. Sure.
Okay.
I'll end the meeting now. So see you, Alok.
See you. Bye.